Good morning, Denise. How are you doing?
Hello, Mr. King. I'm doing good. How are you?
Good, thank you. Um, so, um, I don't know if you just read my email. I just barely typed it. Did you get to see that?
Yeah, no, I just read it.
Okay. I'm
Wonder who
sure.
it was.
Huh?
I wonder who it was. But
Oh,
yeah,
well, I think there's going to be various opinions on which way to go, you know? Um,
yeah, I guess.
So I don't want to make a big, I actually think there's merit to what the person was saying. And so I'm going to try to adjust, and then I can always make the off, I guess, and I can always make the office hours longer if they need to be, and do it that way. And maybe maybe that's a better idea.
I could see why it would maybe get overwhelming for some.
Yeah. So that's what I'm gonna do. And also starting Monday. Good morning, Brian.
Morning.
How are you?
Doing good, and yourself?
Good. I got a notice here. It says your network bandwidth is low. I've never seen that before. I don't know if you're very close to your server at home, or I'm not sure. But anyway, but you can hear me okay.
Yes.
Okay, good. Okay, so let's begin, and we'll start with, so the last part of chapter 8, we had spent a lot of time on Monday, and now I want to polish it up and go into chapter 9. And you'll notice the sections in chapter 9 are shorter and quicker. So chapter 8 is just very long if we want to try to do a decent job. And then that'll pay off when we get into chapter 9, as you'll see. Okay, so let's begin. I'm going to go to my WebAssign. And here we are. So I wanted to do some more problems from this assignment. And let me see here. Oh, also starting on next week, I will already have written the problems out. There's pros and cons to that. That means it will go faster, but it also means if it's too fast, people will have to go back and find that part of the recording that they didn't quite, it felt too fast for them, and then they can hear it again and pause it or replay it or whatever. Yeah. So trying to streamline this to make it reasonable for the majority of people out there. So, and we'll see how that goes, okay? Okay, all right, so let's take a look here. And I know I had told you on Monday, number 10 and 11 were integration by parts. So I wanted to do one of those with you. And then we'll see, oh, and also 13 is not integration by parts, but it is a little strange integration. And 14 as well. So, and then we'll maybe look at another one or two here, okay? So, okay, so let's do that. And perhaps let's start out with 14, okay? So here we go. And so I'm gonna write down the problem and we will get started. Okay. Where am I here? And good morning, Jocelyn. If you can hear me. Okay. Okay, so number 14 on section 8.2. 8. And we have the integral from 18 to infinity of cosine of pi x with respect to x. Okay. Good morning, Jocelyn. How are you?
Good morning. I'm good, thank you.
Good, good to have you here. Okay, so we're working on number 14 on WebAssign, of course. And so let's take a look. So first of all, this is an improper integral, and it's improper because cosine graph does not have any vertical asymptotes on it. So that's not what makes this improper. It's this in upper limit that is not a finite number. It is infinity. So, okay, and so that's what makes it improper. Okay, so it's an improper integral. So what we do is oh, you can't see my notebook. Okay, good morning, Josh.
Good morning.
Okay, so we're just gonna start with 14 and I'm about to switch to my notebook. So here we go. Okay, and that doesn't look too good. And hopefully that's better. Okay, so we change the improper integral with this infinity value, we change it to a letter. And that's sort of it kind of seems like a little mathematical gimmick. And in order to be able to integrate an integral from the theoretical point of perspective, these have to be, if we have any limits here, they have to be finite. And so what we can get away with here is, it seems like a gimmick, but you change this and B represents a finite number. And then that allows us to integrate and then to use the first fundamental theorem of calculus to evaluate it. And then after we've evaluated, it'll have that finite representation with letter B in the answer. And then we're like, okay, we're done, take a breath. And then we can then take the limit as B approaches infinity. So that's kind of the idea in a theoretical sense of why we are able to anti-differentiate this, and we're also able to evaluate it. So anyway, so the limit here is just waiting. And now we evaluate, we integrate, cosine. So the antiderivative of cosine is in our formula sheet. And the only thing is we have a pi x, we have a multiplied constant. So hopefully we're okay. We could rename this W. And if we did that, or a U, then we would have the integral of cosine of W. And then we're gonna have to plop that dW, but you always have to differentiate this renaming statement to get the dW and its relationship to dx. And so we do that. And some of these pieces that we've kind of been doing throughout the course, I'll just go faster on. And the derivative of pi x would just be pi. And then just interrupt me if you have a question. Okay, so
Okay.
we have dW then equals pi dx, multiplying both sides by dx. So then when and we could have done this mentally if we were comfortable, but I'm writing it out. Cosine of W takes care of the cosine of pi x, and the dW is really what this is, which is a pi dx. And so this integral that we have renamed is the same as this integral, but there's an extra multiplied what in here in this dW statement? There's an extra multiplied what? Pi. So we compensated in front with what? A 1 over
Pi.
pi. Okay, is that okay?
Yes.
Okay. Technically, we're not supposed to write the limits of integration here now, because now these are supposed to be with respect to whatever this variable is. So we can kind of informally write 18 and b here, but we're really formally not supposed to, because now these represent w values. There is a way to do that. I'm just not, we just have enough things to do, so I'm not going to show you that unless you ask me like on the online tutoring session or something, and then I'd be happy to show you that slightly alternate way. Anyway, so now we're ready to anti-differentiate it. So we have the limit as b approaches infinity of, and now of course, what is the antiderivative of cosine? It's just of a single letter with respect to its same letter. That's just what, of course?
Sine.
Sine. W, and then we still have this 1 over pi. And now, well, we're not going to evaluate it yet because we have the w still. So we have to go back to our x. So we have equals the limit as b approaches infinity. And our w was pi x. So now we can put here with respect to x, and that was 18, and this was at b. And now use, and see, now we still can use formally the first fundamental theorem of calculus right here, because these both represent finite numbers for the moment. Well, that is finite. B represents any finite number. And then that's like the little catch that allows us to evaluate this. And then we take the limit after that's already been done. And then that's what makes this all legitimate, mathematically speaking. So equals the limit and we input our upper and lower limit of integration, and we're going to have sine of pi b, and then minus sine of pi times 18, we can say 18 pi. So any questions so far?
No.
No.
Okay, very good. So now this has a b in it, so we can't do anything more with this until we take the limit. And then this one doesn't have a b anywhere, so it doesn't change anything if we take, when we say, oh, let's take the limit of this term, because there's no b here anyway. So so this sine of 18 pi, we could put in a calculator and make sure you're in radian mode, and that would do it. Or just remember that sine is y over r, which is the alternate to opposite over hypotenuse. And at 18 pi radians, this is 0, 1 pi, 2 pi, 4 pi, 6 pi. So eventually we get to 18 pi, and it's still right here. So the sine value is the y value, which is 0, over the radius on this unit circle is 1, so we get 0. Or you could just put it in a calculator. So minus 0 for the sine of 18 pi. And now there's still this 1 over pi in front, multiplied. And now we are ready to take the limit here. So sine of pi times b, but as b goes out forever and ever, make larger and larger. So I want to pause and show you on Desmos what this involves, and I hope that helps us. So let me do that. So we have the graph of y equals sine of pi x, and we're interested what happens to sine. Here's the origin, but as you go out to infinity, yeah? So here is this sine of pi x graph. It's just compressed. This multiplied pi compresses all these oscillations. But we do know, we can see here, or we can remember from our trigonometry studies, that as long as there's no multiplied number in front of the sign, then the sign goes up to 1 and down to -1 and then oscillates forever. So this is why I wanted to do this problem, was because of the moment right here when we have to take the limit as b approaches infinity of sine of that pi b. So this was the whole, again, the whole reason why I wanted to help you, was this moment right here. And so what happens to this sine graph? It would be the same with the cosine graph. These oscillations don't get smaller and smaller, closer and closer to some value here, like closer to 0 or something. They just keep oscillating forever. So they never settle down towards any finite number, and they don't go up forever to infinity. They don't go down forever to negative infinity. So this limit is none of these, what we were calling in this class a determinate form, which is finite number. The limit gets closer to some finite number, or infinity, or negative infinity. And it's also none of these indeterminate types. Like if you put infinity right here, except we had a b is all, but if you put infinity here, as you go out forever, you don't get 0 over 0 or infinity over infinity, which would be a friendly indeterminate type, where we could use L'Hopital's rule. It doesn't give us any unfriendly indeterminate, where we can use those suggestions to manipulate it into a friendly indeterminate either. So this limit right here, it's not determinate and it's not indeterminate. It's not a friendly indeterminate. It's not an unfriendly indeterminate. It is an oscillating type of trying to categorize it, but there is no other way to say it, because it's not determinate and it's not indeterminate. So it's just an oscillating type that has no determinate answer. So what we say here is, when we write it on our paper, this limit does not exist, yeah, but it's not because it's indeterminate or anything like that, and it's not determinate either. It's just oscillating forever, up and down to 1 and -1. So what we're going to say for this limit is it does not exist, it's not determinable, and it's not indeterminable either. It just doesn't exist, okay? So any questions on that idea?
No.
Why can't you use the squeeze theorem?
That's a good idea. You could use the squeeze theorem if you get oscillating on, and we're going to have a problem like that later in a section again, and we had it last week. If that's when this was divided by an x right here or something. So if we would have had sine, so that's a very good question. If we would have had sine of pi x, oops, x divided by x, that's a different situation because I'm going to erase this one. So notice what's happening here. As you go out forever, it is oscillating. It's going up and down, but notice, are these oscillations staying the same height and the same height underneath forever, or are they getting smaller? Aren't these oscillation heights on the top and the bottom, aren't they getting smaller and smaller?
Yeah.
And the reason it is because you're taking the same sine of pi x and you're dividing it by x. And x is getting bigger as you go out. So when you divide by this bigger number, those oscillations that were going from 1 to -1 on the red graph, when you divide them by a bigger and bigger number, the answer becomes smaller and smaller. And that's why these oscillations are diminishing in their height or their amplitude. And that's why, and then when we did take the limit, we had oscillating behavior between -1 and 1 on the top, and on the bottom we got infinity. And that's when we could, that was not a friendly indeterminate. It wasn't an unfriendly indeterminate. So we couldn't use any strategies there that we have been practicing to take the limit and analyze it further. It wasn't determinate. The answer when you had this problem before, it wasn't determinate either. If you substitute infinity in here, you don't get infinity only or negative infinity only or a finite number. You get oscillating behavior on the top and divided by infinity. And that's when you had to use that squeeze theorem where we use the double inequality. And then, does that answer your question?
Yes.
Because there is no x right here on our problem on the bottom, is there?
Yeah.
So that's why,
Yeah.
that's, if I were to go back and show you the paper with the squeeze theorem, it would have that where we had it divided by x, and that's what allowed us to squeeze it. It squeezed closer and closer to 0 from above and below. I just don't know where I have that in my paper here, but in my notebook, but it's somewhere there. So, and we're gonna see that again in 9.2, and I'll show you that again.
Okay.
I hope I kind of answered your question.
Yeah. No, yes, you did. Thank you.
Okay, so that's why when we go back to our problem here, and we get this part right here, the limit as b approaches infinity of just sine of pi b, then here it's not divided by x, because then we could use the squeeze theorem, Jocelyn, okay? But here, it's not divided by x. I think it was Jocelyn, I'm not sure.
Yeah.
You asked that, okay? So now here we're just gonna put, this is, it has this oscillating behavior. It oscillates. So we literally, when they have this oscillating behavior, and the most common ones will be with sine and cosine by itself, okay? Well, and if it's divided by x, it's still oscillating on the top, but then we can use a squeeze theorem. This oscillates between -1 and 1 forever. As b approaches infinity. So, because of that, we can say, or this 1 over pi times this inside, this is not any number. This is not determinate. And it's also not indeterminate. Friendly indeterminate, unfriendly indeterminate, it's none of those. And so there's nothing we can do because that graph does never settle down. And so therefore, we can only say the limit does not exist. Yeah, there is no determinable limit value for this limit. Okay, and the 1 over pi doesn't have any influence because this is not a number, or if that was an infinity, that would be determinate. And infinity times 1 over pi would still be infinity. Infinity times negative infinity, if that's what we would have gotten, times 1 over pi would have been negative infinity. And if we would have gotten a finite numerical answer here times 1 over pi, well, then we could actually multiply it and have a new finite numerical answer. So I hope we understand that this limit does not exist, and we understand what that means. So you can just say, therefore, the limit does not exist. Okay, it is not determinable, which means, and it's not indeterminable. If it was indeterminable, that means we could try to still do more work to figure out what is the determinate answer. So so that vocabulary can be confusing, but I hope you understand. Any questions there?
No.
No.
Okay.
No.
So anybody?
No.
Okay. So we go back and we go to our WebAssign, and here then, so the integral, and you may remember the other day I wrote some notes that before I had written, if it diverges, that means you would get, because you got infinity or negative infinity, which is still true, which is one of the determinants, but it's just not a finite number, so then you would say diverges. Well, here's the last other possibility when you will say diverges, and that's when you have that oscillating behavior. So this is still diverges, but for the oscillating reason. So we type diverges and submit. And there we are. Okay, any questions here?
No.
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 Excellent. So let's go on. So I wanted to show you this one and the one of those. We'll do one of these two. They're kind of the same, or they're close to being the same. This one has a higher exponent. And we can even use tabular integration for this one, or even that one. You don't, this integration by parts will just require one iteration, or one of the integration by part processes, and this one would require twice. And then we talked about that, and it's been a while. I think that was actually the first section in our course when we did this integration by parts. And then I mentioned there's this other way to do it faster, the tabular. So this gives us a chance to review that as well. Okay, but first well, I just mentioned it, so let's just do it. Okay, so number 11. And 0 to infinity. So that infinity right there is what makes this improper. If this could ever be undefined on the bottom, this e to the negative x could be moved to the bottom, but even e to the x on the bottom can never be 0. E to the x is always going to be e to any number is always going to be a positive number. So this is never going to have a vertical asymptote, but it does have the other possibility of why it can be an improper integral, and it's because of the infinite limit of integration. It could be infinity or negative infinity or both. So we have x squared times e to the x with respect to x. Okay. So we could look at the graph. Y equals x squared. Oops, that doesn't help. Capital. Y equals x squared times e to the negative x power. And here is that graph. And we're only interested from what is this area from 0 right here. There's a little sliver there, forever to the right. And you see there's this infinite horizontal sliver. And if you zoom in enough, you'll see that it never touches the x-axis. So this is an infinite sliver, although it's smaller and smaller sliver of area, so to speak, but it does go on forever. So again, there are no vertical asymptotes or infinite discontinuities on this one, but it is improper because of that reason I just said. This goes on forever to the right. So the question now is, what happens when we start to add up this area forever to the right? Does it add up and get closer and closer to some finite numerical value? Well, that would be a determinate limit answer or value, and then we would say converges. Does it get closer and closer to 9? That's what I just keep saying 9 because that's the one I showed you the other day. Or does the area pass 9 and get, maybe it gets closer and closer to 15 and never makes it to 15? Well, that would still be convergent. Or when you add this area here is above the x-axis, so it's going to be a positive area, not a negative one. And maybe this area, as you go out, it gets to 9 square units, and then 10 square units, and 100 square units, but never, it just keeps getting larger forever, and that is the infinity determinant value. And that's determinant. We can determine and state, determine meaning we can state the value of this improper integral, its infinity, and that is correct. I mean, that may be the correct answer, but we still say, because it's not a finite one, it's still determinant, but we say the improper integral diverges instead of converges. So any questions about that idea again?
No.
So that was kind of a lot of words there, but I hope that makes sense. So we could always analyze it, and we could look at the integral from 0, and at 0 there is no vertical asymptote. Sometimes there could be, but notice here, there's no vertical asymptote. It doesn't go up that way forever or down that way forever. So there is no infinite discontinuity or vertical asymptote, which is what I meant by when I was trying to explain that the denominator here, even if you move this down underneath, it can never equal 0, because e to the x underneath is never, e to the x is never going to equal 0. It's always a positive number. So anyway, so 0, and let's just pick some number. If we only go out to 3, and that's going to be this area right in here, only this area, and that's a finite amount of area. So that would be something that we would have done, and even in the first section of this second semester calculus, because we could have integrated with integration by parts and evaluated it. But let's let the computer do it. And then with respect to x. And so this area right here, class, it equals, this probably goes on forever, but they rounded it to this many digits past the decimal point, and that's what the area is. Now the question is, what happens if you go out to 4? Well, you can see that's going to be more area. So of course the answer is going to be bigger. And if you go out to 5, that'll be bigger yet, and to 6, and so on. But the question is, now this starts to become infinitely smaller and smaller. So that's the interesting part. Does it get closer? It keeps adding more area, but does it get closer and closer to some answer like 9? Or does it pass it? And it passes every finite number, and therefore you have an infinite amount of area. So that's kind of a, if we're kind of curious about this, it's kind of fascinating to think how can it, what makes one time equal a finite number, and another time it just keeps getting bigger and bigger to infinity. So that is interesting, I hope. So let me just change this to a 4. Oops, to a 4. Well, and of course, out to 4 is more area. So of course it's going to be a bigger answer on this definite integral. Yeah, so this 1.52 is bigger than 1.15. And if you go out further, yeah, and now I'm just gonna, so we could just repeat and say 5. Well, it's bigger yet. And now I'm just gonna go like this. So we got 1.75. Now what if we go, say we go out to 20. Well, now it's at 1.999999. So if we go all the way out to 20, yeah, you can imagine what I'm just gonna clear this picture. So you can imagine if we go out to 20, here's 20. So all of this area is increasing, increasing, increasing. And when we get out here, the area is this 1.9999. So now the question is, if we keep going past 20, the area is gonna add more area to it, but is it gonna add enough to make it to 2 and surpass 2 and make it to 3 and surpass 3 and so forth? So what would you guys guess right now is gonna happen? You think it's gonna, if we go out further, say we go out to 100 right now, you think it's gonna make it to 2 and pass it, or just get close, if you had to guess? Or it converges, meaning that it gets closer and closer to 2 square units of area, but doesn't pass it? What would you guys guess?
It just gets closer to 2.
Yeah, so that would be my guess too. Let's find out. So let's say we change this to 100, and the computer gave up already and just said it was what?
2.
2, but it isn't really 2. If we could look inside this computer, it's like 1.9999999 for long ways. But it never actually makes it to 2. It's just the computer's limitations on how many digits it's willing to show here, and then it eventually just rounds it to 2. So if we went out to 50, it still gave up. Yeah, so this one converges. Later on they study, does this one converges to 2? And does it converge quickly or slowly, or whatever that means? Well, it doesn't take long at all for this to get closer and closer and closer to 2. So here the computer just rounds it. But it's not like we had to go out to 1,000 or 1,000,000 and then it was still, I hope that makes sense. But anyway, it's not really that critical to understand for the problems here. But so if we go out to 30, it doesn't quite give up and say 2 yet. Yeah, so I guess once this gets to a 9, the computer just gives up and says a 2. So does that make sense?
Yeah.
Okay, so now we know this area, this improper integral, this infinite horizontal stretch of area here is going to converge towards 2. It actually never makes it to 2 because you cannot make it. It's not like you can say, oh, I made it out here to infinity on the x-axis and that's when the area became 2, because you can never make it out there to infinity. So But the idea forever and ever and ever, this little stretch of a horizontal infinite sliver of area gets closer and closer and closer to 2. It never actually makes it to 2, even though the computer said 2 right here, but that's because of its limitations. Okay, so I hope that, and that idea is important for us to understand, because, well, not only for this, but for what's coming. So, okay, so now we work it out. And I have the integral here, and we already know from the graph it's going to converge to 2. Converges towards 2. And instead of saying equals 2, that's what they end up saying, but I hope we understand, because this is improper, it means that as you go out to infinity, which you can never get to, the area gets closer and closer towards 2 square units of area. And it's not always considered area in applications. It could be all kinds of things like force or how much work and so forth. Anyway, so this is an integration by parts. There's 2 parts here. You cannot use a renaming technique and let u or w equal one of these pieces, and then the derivative is the other piece. This will not work. It's not a formula in your basic antiderivative formula sheet. It doesn't have factors in the denominator where we could use partial fraction decomposition. One of them, they could be linear or irreducible quadratic. That was a section. It's not anything with a square root where we could convert it into a trigonometric form. It's none of those, and therefore we're stuck unless we can use integration by parts, and we can. One of these pieces does differentiate down to 0. This one does. And this one we can anti-differentiate it continually. So this is an excellent problem to use tabular integration instead of doing the integration by parts. So I would like to do that, and we're going to use, instead of the longer process of integration, instead of using the longer process, which would be 2 iterations of integration by parts, and it would be, as I mentioned, 2 iterations of that, which isn't so bad, but this problem, or this integral, can be done using the shortcut method tabular integration. So it's easy to, we get a little rusty in our minds when we haven't done it in a while. So it's only natural. So that's why I'm picking this problem. Okay. So tabular integration. So this is how it worked. You put the one that can anti-differentiate here. This was like our dw, and this was like our, oh, I'm I'm sorry. Gotta get my letters straight. It depends. I mean, we can use whatever letters. Our DZ, and this was our W. And we could have picked e to the x, negative x for this, x squared for this, which we will, and then did it this way with 2 iterations. Or we can say, hey, look at one of these differentiates down to 0, and the other one can be anti-differentiated. So this is a great problem to do, to use this tabular integration. Okay, so we differentiate. Brian, what's the derivative of x squared, of course?
I'm sorry.
Brian? I'm sorry?
The derivative of x squared
Yeah.
would be
So use the power rule, bring down the 2.
2x.
And what's the derivative of 2x?
2.
And the derivative of 2?
0.
And that's where you stop once you get to 0. The antiderivative of e to the negative x well, the derivative of e to a single letter just goes back to e to the u. It's just you're going to be off by a negative here. So if we use u equals negative x, then du is equal to -1 dx. And if we write our integral e to the u, plop the du, e to the u takes care of e to the negative x. The du has the dx that was here, but an extra multiplication of -1. So to compensate for that, we divide or multiply by a -1, either way. And we get -1 times the integral of e to the u, and which is just e to the u, which is just e to the negative x. So any questions with that?
No.
Okay, so now here we're going to anti-differentiate each time. So Denise, can you help us here? The antiderivative of e to the negative x, well, we just did that, and that was what, of course?
Negative e to the negative x.
So every time we anti-differentiate e to the negative x, we write down this answer. If there's a number multiplied in front already, then that's just sitting there waiting. And yeah. So now we have to anti-differentiate this again. And so Denise, what's going to happen when we anti-differentiate e to the negative x? We still have this -1 that was waiting. That's sitting there in the front, but what's the antiderivative of this e to the negative x again?
The negative e to the negative x.
And this negative here times this negative here would be what?
Positive.
So we kind of like, oh, we could have done that on the side of our paper, but so really we went to this, but now we're here. And now we have to keep anti-differentiating until we get to this 0 spot. So we anti-differentiate one more time, and Denise, of course, what's that going to be still?
The negative e to the negative x.
Any questions here?
No.
Okay, does anyone remember, does anyone happen to remember what we do next? We have to connect these somehow.
Yeah, you connect the x squared to the second integral.
Very good.
And then you, I don't know if you multiply by a -1 or you, I forgot. I'm not sure.
But that's very good. The first one is times a +1. And always. And the second one is going to be times a negative 1.
Negative.
And it alternates. So someone just discovered this and thought it was helpful, which it is. And so it was published, yeah? Okay. And now we have one more to go. So remember, it's x squared times 1, or you can think of it however you like, but these three are multiplied together. So if you want to say x squared times 1 times this, that's fine. If you want to say x squared times this and then times 1, that's fine. So it's commutative. Multiplication is commutative, so it's either way. And now we have this is why you don't need to go any further, because if you did anti-differentiate again, you could do this forever, but we're going to have 0 times whatever ends up here, and that'll be 0, so there's no need to keep going. So that means we are done. And if you get 3 arrows, which we did, and that means if you would have done it by hand with the regular integration by parts process, it would always be 1 less than the number of arrows here. So it would have been 1 less than these 3 arrows, which would be 2 iteration processes, and then we would have been done, which is what I wrote up here. Okay, so the integral, the antiderivative of this is going to equal this expression with these 3 arrows, these expressions, those 3 multiplied expressions put down, and then we'll have to evaluate it, but because it's improper, we're going to say 0 to b, and then we'll put a limit in front as b approaches infinity. So, so the integral from 0 to infinity of x squared times e to the negative x equal, with respect to x, equals the limit as b approaches infinity of, so we already anti-differentiated it. And, sorry, I'm making it worse. But anyway, so, and now we can put all these terms down, and then we're evaluating it from x equal to b and at x equals 0. And here we should have our 3 terms together. So, Joshua, can you help us? So what's going to go right here? It's going to be the first arrow, which are these 3 things multiplied together. So, Joshua, are you there?
Yes.
So what's going to happen when we multiply x squared times 1 times negative e to the negative x? And let's put this e to the negative x last and put the x squared in front and any number in front of all that.
It's just going to be negative x squared times e to the negative x.
Very good.
Why is the x squared negative?
Because this was not negative, you're correct. But right here, the antiderivative of e to the negative x was this answer, which is kind of looks a little sloppy here, but it's right here. Negative 1 times e to the negative x.
Oh, so that negative 1 goes to the x squared?
So that negative 1 is multiplied by this 1 times the invisible multiplied 1 in front. And all that becomes what, Denise?
Okay, negative x squared.
Does that make sense?
Yeah.
Okay. Okay, Josh, keep going. What are we going to multiply now?
The 2x and the negative 1 times -1 e to the negative x.
Now remember, you're close. This part cleaned up.
Okay.
Just this
Yeah.
part, right?
So
Maybe
then it's going to be
right, and I didn't hear you correctly. So say it again. It's 2x times what?
e to the negative x.
Yeah, times the -1.
It's going to be -2x.
So good. So negative 2x e to the what?
Negative x.
And then the last term, Joshua, this time 2 times 1 times -1 e to the negative x, that's going to become a
-2 times e to the negative x.
Any questions here, guys? Girls?
No.
No.
Okay. Now we are ready to input the upper limit of integration and the lower limit of integration. And then when that's all cleaned up, then we take the limit. Okay. But I just want to point out, let me think for a second. I'm looking ahead in my mind here, and I want to make sure, because this can get a little bit messy. Okay, so, so one thing we could do would be to factor out e to the negative x on all three terms and write it out in front. But I don't want to take the time to show you on this recording to show you what makes that worse. It turns out that, and I don't mean to be rude or anything, I'm just trying to look at the clock. It's better if we just move this e to the negative x, and this will move down underneath on this one. It'll move underneath on this one, and it'll move underneath on this one. And that's going to make it easier, because what do we want to get, class, when we take the limit? Do we want it? Well, it'd be great if it's just determinate already. If it's oscillating like the sine one, then we're just done and we say it doesn't exist. But if, what else could happen if it's not determinate and being done, if it's not oscillating only being done and say does not exist, the other possibilities are unfriendly indeterminate and friendly indeterminate. Which one do we always rather have between?
Friendly.
Friendly. And so what my mind was trying to think was, if we move this underneath, won't we have a fraction then? Yeah.
Yes.
And what will happen, and same thing here, it'll be that's a negative x squared over, what will happen underneath? It'll become e to the what?
To
E to
x.
the x.
And what my mind was trying to think was, what's gonna, and we do the same thing on the next term and the next one. What's gonna happen when you take the limit as b approaches infinity if we write it in a fraction form on each term? What's gonna happen right here? What's infinity squared?
No.
Infinity.
It'll be infinity times negative will be negative what?
Infinity.
Over to the infinity will still be what?
Infinity.
Infinity. The exponential graph e looks like this. Just e to the x by itself. So as you go up forever for e to the x, this just goes up forever. So it's always going to be e to infinity. So here we would get negative infinity over infinity. Now that's indeterminate, but is it an unfriendly or a friendly?
Friendly.
Friendly. Remember, any kind of infinity, negative or positive over, again, any kind of infinity, is friendly indeterminate which is always good news because now we can use what famous rule?
L'Hopital?
L'Hopital. And so this would be a physical derivative, negative x squared,
Negative 2x?
negative 2x. The derivative of dx is just,
E to the x?
and then we will be able to reduce this down into a determinate form rather easily. So that's why right here, this is kind of a mess right here, but it helps if we understand that taking a limit, and when we plug infinity in, we want to get it into a friendly indeterminate, and so it's best if we put this e to the x underneath on all of them. And okay, if you
Okay.
factored out an e to the negative x, now you would have a factor times another factor, and that's not going to give you a friendly indeterminate. It's going to give you one of the unfriendly. Then you have manipulated it a different way as anyway. So what I'm suggesting is if we can see that this moves underneath, which you can because that's a negative x, then you get this situation which is a friendly indeterminate, and it just makes this faster to get done. So that does take a little bit of insight and looking ahead, but that's another reason why I wanted to help you with this problem. Okay,
Okay.
so let's do that. So we're going to have a limit and Jocelyn, can you help us with these terms here? So we're going to get what here? Negative x squared.
Negative x squared over e to the x,
Good.
and then minus 2x over e to the x, and minus 2 over e to the x.
Very good. From x equals 0 to x equals b. Now I hope you see when we put the b's in, I mean, there's going to be a negative b squared over e to the b. But when you take the limit, you're going to get that negative infinity over infinity on this term, and then you're going to get something similar on this term, and then we're going to be able to use L'Hopital's rule. So that's what I was trying to say. So let's continue here. So Jocelyn, do we take the limit yet, or first put in the, or do we?
Mr. King, for some reason it sounds like if you're chopping off from your audio a little bit.
Oh, sorry. So I don't know, maybe my body is getting further away from my mic. Is it any different? Am I still choppy?
Yeah,
It's,
It's still choppy?
yeah, it's still very choppy.
Is that what it wanted to just send in your chat? Oh, I guess you send it to everybody else. Okay. I do. The other times that would have happened, I'm not trying to remember what I tried to do differently. I know there's a setting, but I already know that part's okay. And the only thing I can do is stop it and then come back and we can see what happens. Okay.
Okay.
So what I'm going to do is stop it, and then invite you back, and then we'll continue, and I hope it's better, okay?
Okay.
Okay.
Okay, okay. So, let me just try one more thing first, because I really doubt that did anything different, did it?
No.
No.
Okay, so I'm gonna end it and then invite you right back, okay?
Okay.
Okay.
Bye.